Good afternoon, everybody. So we just heard from Michael on policy trends for microgrids. We heard from Peter on funding mechanisms, and we just heard from Richard that our power grid is really fragile. And so I'm going to talk about another type of threat to power grids and microgrids. So this talk is going to give you a flavor of what's happening out in the world in terms of cybersecurity. And let me just flip to the agenda there. So how does this new cyber landscape will put smart grids and microgrids at risk, how we might think about dealing with this, and I'll provide some proposals and approaches for addressing the security problems inherent in these that we see today. So hardly a day goes by that we don't hear about a new cyber attack. In the news, we're constantly seeing more and more dangerous intrusions into networks, and it's kind of like the new normal. It's gone to the forefront of our collective thinking about how to protect critical infrastructure. So from identity theft to ransomware, and now with the successful attack on the Ukraine power system that happened just less than 9 months ago, these attacks are becoming more kinetic. And by that I mean these attacks have the ability to interfere and even damage operations that people depend on for their lives. So this is almost like a war, if you think about it. So we hear in the news constantly about the Internet of Things, and really what this means, it's a marketing phrase, right? It's really just a pitch that's talking about machine-to-machine communications, or how machines are talking together without humans in the loop. And when that happens, a lot of trouble can start. It's like things are not supervised. So although there's many benefits and opportunities, such as improved performance, cost, savings, efficient operations, this emerging trend of machine-to-machine communications is greatly increasing the size of what we call the so-called cyber attack surface. So the attack surface really represents the potential number and variety of vulnerabilities for a given domain, including smart grids. So understanding this should inform our approach to cybersecurity. So these attacks are becoming much more effective. Here's a list of several. Everybody's probably heard of Stuxnet and how it impacted the nuclear enrichment facility in Iran. Even though their operational network was not connected at all to the Internet, it was supposedly, quote-unquote, air-gapped. So in addition to Stuxnet, there's other viruses out there. Flame, Dooku, Gauss, there's Black Energy, there's all sorts of bad things out there. And you may have heard that weak security in smart meters in Puerto Rico allowed consumers to steal $400 million a year in power. So not only outside attackers, but insiders can cause just as much or even more damage to the networks. One lesser-known attack occurred in Australia. A disgruntled employee wanted to get even with his employer, the Marucci water treatment facility. And so what he did is he took a simple two-way radio and a laptop. He, through a control device, he issued radio commands that caused 210,000 gallons of sewage to dump into a town. This killed marine life and caused people to move out of their homes. So when you talk about a kinetic attack, you've got that right there. So who launches these cyber attacks? Well, many types of people, from kids, criminals, activists. They all have varied motivations for doing so, from gaining notoriety, financial gain, for causing harm, or even just for fun. In terms of critical infrastructure networks, we are seeing, such as smart grids, we're increasingly seeing the involvement of nation-state actors working on behalf of U.S. adversaries. So let's take some advice from some top folks in the industry and in government. Admiral Michael Rogers, who heads the NSA and the U.S. Cyber Command, famously gave an ominous warning that China and a couple of other very high-tech countries have the capability to take out our power grid. Former CIA Director James Woosley has put the power grid at the top of the nation's vulnerability list. He's very concerned that if attacks disable just a few key parts of the network, they could take out the entire power system for an extended period of time. Now, John Wellinghoff, the former head of NERC, has suggested that the use of distributed microgrids might be a possible way to help mitigate cyber threats through a fundamental realignment of the power grid. So in this way, although each microgrid, individual microgrid may be vulnerable, no single attack would take out the entire system. So in a sense, microgrids can help add resilience to the entire power grid. So using microgrids doesn't eliminate the problem, but it changes the problem. And perhaps it changes the problem in a way that is manageable and will make the entire power grid more resilient. So I don't have a definition of the power grid, but I have some pictures here that I got from a report from Sandia Labs. So we'll take a brief look at how it operates. So here we show a normal day-to-day operation of the power grid. All the loads are grid tied to a main feeder supplied by a utility. I don't have storage, but I've got some of the other components. So right after there's an outage from the utility, this is what the microgrid would look like. Not only the loads, note that only loads with the UPS system are going to run at that point. In this case, building B in this picture experiences no power outage. So next we have normal emergency operations. And what happens here is Tier 1 and Tier 2 loads are now individually powered with diesel generators. And next, once the generators are synchronized, all the Tier 3 loads are disconnected, and backup generators energize the microgrid to power the Tier 1 and Tier 2 loads. Then unnecessary distributed energy resources can be cycled down, and the microgrid will operate more efficiently. And then finally, we have the microgrid conditions with a connected renewable energy source. So after the microgrid's energized, these inverter-based renewable resources will connect the microgrid, signaling its full activation. So as you can see, what I just showed you is there's a ton of machine-to-machine communication going on, a ton of automatic control that occurs. And this is crucial for this to operate. It's also very easy for a cyber attacker to come in and look at all of those network commands and try to take that out. So in order to ensure that these distributed microgrids can operate effectively, you must make them cyber secure, and this will help us to realize the vision of John Wellinghoff. Now, there's some fundamental challenges with what I call ICS security, industrial control system security, because really it's an industrial type control system that we're dealing with. So today's control technologies, ICS technology teams are focused on operational priorities. All of you in this room maybe are focused on operational priorities, leaving cybersecurity protection mainly up to your IT team. Commonly used industrial protocols don't have built-in cybersecurity features such as encryption and authentication. So many industrial control systems never have their vulnerabilities patched due to either an absence of an existing patch or maybe for operational priorities that will delay or preclude patching the system. Now, Sandia National Labs in 2013 produced a microgrid cybersecurity reference architecture. And in this architecture, they have a threat model and an IA approach for compliance. The emphasis in this report is on segmentation of the networks and enclaves based on the various functional domains. And we believe that this approach is sound and still applies today. In this talk, we want to suggest some updates and recommendations, pointing out some of the recent guidance from the Department of Homeland Security and reemphasize some of the best practices that come out of industry, cybersecurity guidelines, for example, from the International Society of Automation. So since it was first published, there's been several changes in the environment and in the cybersecurity environment. The original authors of this report had determined, they understood that the Department of Defense's DIACAP, which is their accreditation process, is going to be migrating into the National Institute of Standards and Technology's risk management framework for network assessment and authorization. So they anticipated that, and they said that they needed to refresh this at some point. They also wanted to add some stronger design principles to this standard, and including monitoring and reconfiguration to help with the resilience of cybersecurity. And they also wanted to add assessment of information assurance controls, and they wanted to look at industry best practices. So let's take a quick look at the RMF transition. So you can see the two processes side by side here, and the transition from DIACAP to RMF has really changed the emphasis from a pure validation focus to more of an assessment and audit focus. And these standards are all online, and you can look them up, and the RMF is very well detailed. So with this new focus, the DIACAPS, which depends on what's called DoD Instruction 8500.2, there's tons of things you can read on this. That control set was specified for its implementation, and that's shifted over to NIST. And NIST has a special publication, 800-53 control set, which to match the controls used by the rest of the federal government. So it's going to unify and standardize the controls that are used. And note that unlike DIACAP's somewhat paperwork-intensive process, the RMF has built in a continuous monitoring provision into the standard. And this continuous monitoring standard is going to help to catch security-relevant events and also help to extend the accreditation period. So this is much better for the power industry and people who implement microgrids. And RMF has also a much more fine-grained categorization methodology than DIACAP's former mission assurance categories, or MACs. Another standard that really is indispensable, say it's a must-deploy practice, is the IEC 62443, which is formerly known as the ISA 99 standard of the International Society of Automation. Now, this prescribes clear definitions of zones and conduits in a network, and I'll have a picture of that, and what a traditional enterprise IT person would refer as to network segmentation. And this will help to establish better control over access and security in a microgrid environment where you have ICSs and SCADA-like networks. So in terms of recommendations to further secure your environment, you really want to identify just a few applications that you're running, and you want to identify the zones, legitimate applications that run in specific zones in your network, block everything but legitimate microgrid industrial applications commands, and use firewalls and packet monitoring to enable you to easily implement these tight controls. So I'll show you a picture of that. So this is a typical industrial control system network. It could also represent some of the types of equipment we may find in a microgrid. The important thing to note here is that there is a lot of machine-to-machine communication in this network. And zones define groups of assets based on functionality, and those are kind of color-coded into different groups of zones. And then we have conduits between them, level 1, level 2, and level 3 conduits that connect those zones. So by partitioning our network like this, we can put specific connections into specific areas. Now, zones should always be chosen to define the maximum size of an area where an acceptable impact to the network could occur. So you want to say, okay, if trouble starts in this zone, I'll contain it to that zone and it won't spread. That's important because these malware attacks can migrate throughout your network. So let's look at an outside attack coming from an enterprise network to a control network. So at the edge of the network, that's where you might be connected to the internet. You have an attack coming in, and this increase in connectivity between the IT and the operational technology environment is really a key factor in the exposure of these ICS networks to these new risks. So a real-world example of this, and I kind of pulled some of these from that other page that went by fast, is the Shamoon virus that infected 30,000 computers in an enterprise network at an oil company out in Saudi Arabia. So the entire enterprise network went down, but this attack did not make it into the control network, which is a good thing. So you can employ some cyber strategies to fight these types of things. You could put a next-generation firewall in, but next-generation firewalls may not be able to handle some encrypted traffic if you get attacked with encrypted traffic. You can put in data diodes, which is a good thing to do. But that may limit some of your operational capabilities, so it's not a perfect solution. You could use virtual private networks or VPNs for remote access. And these are useful, but you need to be sure that the connecting computers that they're connecting to have not been hacked. So that's some strategies, but it may not be perfect. So attackers could also introduce their own device to create a backdoor or rogue control point in the network. And this is very easy to do. If you've seen these devices called Raspberry Pis now, they're $35 computers. You can install them in the network, and you can wreak havoc on it. We previously mentioned the Marucci water attack in Australia, where the person used a rogue wireless connection. So, and that comes up fast. Unfortunately, the animation moved quickly. There's also a backdoor attack occurred at Target. In that case, the device wasn't implanted, but a trusted third party connected to the network, a vendor, and he had valid credentials, but he had malware in his computer, and it inadvertently put a backdoor into the system, and it stole thousands of credit card identity and credit card numbers. So in this case, the CEO of the company had to resign. So the cost of cyber vulnerabilities can be very expensive. So you can try to prevent these rogue devices in your network. There are some protections that you can do. You can use what's called MAC address filtering, although that could be easily spoofed by a determined adversary. You can use port authentication with protocols such as 802.1x. That could be bypassed with cheap hardware taps like the Raspberry Pi, and there's some administrative overhead with that, as well as if you try to use encryption. I recommend doing these things, they're just not foolproof. So not only the enterprise can be attacked, but if an attacker gets in and launches and compromises an internal computer network, they can get into the control system. And this happened with the Configure worm. That's an example of an attack deep into an industrial network that flooded the network with unwanted packets, compromising communication with what's called programmable logic controllers, or PLCs, at the edge of the network with detrimental effects. So some things that should be done are to ensure that all the patches are up to date on all the machines and use the latest antivirus protection. It's not going to solve everything, although I've been into some industrial control systems and I've seen all sorts of outdated operating systems used for convenience and legacy reasons. The system works, so they don't change it. But even with the latest antivirus software, that's useless against zero-day attacks. And those are attacks that have never been seen before, so there is no virus signature to detect them. And you can disable external ports, putting PLC firewalls there. Those are great approaches too. Again, not foolproof. So once malware gets into the system, all bets are off. And we know with Stuxnet, that got into the system, and that was the end of it. So again, updating the antivirus is very important. And another thing that you can do that I recommend is adding deep packet inspection. Deep packet inspection can look at the industrial protocols and parse them, and it can detect malformed commands or rogue commands. With this sort of packet inspection payload, the protocol is parsed, but you need to have extensive training configuration to do that. So if a new vulnerability is discovered and a patch is unavailable, running the critical system is risky. Stopping operations is unacceptable, so many operators will choose to run the system anyway. That's the sad truth. So there's really no good options, in a sense. Stop operations, run at risk, or try to add some new detection rules which could disrupt your operations. So feel a little bit hopeless, but there is some hope. From the DHS, hopefully. There we go. The DHS came out with the 7 steps for protecting industrial control systems. And with these 7 steps, they found that 98% of all the ICS CERT vulnerabilities found in 2015 could have been stopped. So what are these 7 steps? Application whitelisting. This is a proactive security technique that allows a limited set of approved programs to run, while all other programs are automatically blocked, which includes most malware. That is, you only run approved programs and block everything else. So, of course, proper configuration management, ensuring that only approved and secured applications are run, reduce the attack surface by locking down your unused ports, build a defendable environment using the IEC 62443 zones and conduits that we talked about, manage your authentication, only grant privileges to users that are required, and nothing higher than that. Secure remote access. Avoid all persistent external connections to vendors. And then monitor and respond. Continuously monitor IP traffic, including deep packet inspection for industrial control systems with specialized protocol parsing. Also watch out for the traffic between the zones, ensuring that a compromise of one part of the network cannot spread. Also, you should keep in mind that you need to do third-party independent validations, and I recommend NIST's FIPS 140-2 standard for encryption and the common criteria through the National Information Assurance Partnership for overall IA. So the key takeaways from the presentation are monitoring. It's critical for an industrial control system or a microgrid. It's important that you know what to monitor and have this continuous monitoring strategy for all your machine-to-machine communication. Define your zones, monitor from perimeter to endpoints. Bridge the communications between the IT and the OT folks. Application whitelisting is essential. Monitor traffic for malicious connections or content. And where possible, authorize and authenticate devices on your network. Ensure the products are accredited by trusted third-party entities. So with NIST's FIPS 140-2, NIOP's common criteria, along with the risk management framework, best industry practices like DHS's 7 steps can help ensure that microgrid networks implement robust and resilient cybersecurity. Thank you.